Find the design strength in pounds. In this problem, a 6 by 6 by 1/2 L-beam is subjected to a load P. The yield stress and ultimate stress of the steel are provided, as well as various dimensions of the bolt hole size and their locations in the beam. The design strength of the L-beam equals the smaller of the design strength of the beam yielding and the design strength of the beam fracturing. The resistance to yielding equals the resistance factor for yield type failures, which equals 0.90, times the nominal resistance for a yield failure, which equals the yield stress, Fy, times the gross area of steel, A gross. The problem statement provides the yield stress as 36,000 pounds per square inch. And we can look up the gross area for a 6 by 6 by 1/2 L-beam, which equals 5.75 inches squared. After plugging in these three variables, the design strength resisting a yield failure equals 1.863 times 10 to the 5 pounds. Next, we'll compute the design strength for a fracture failure. The resistance factor for a fracture failure equals 0.75. The nominal resistance for a fracture failure equals the ultimate stress in the steel times the net area times U. From the problem statement, we know the ultimate stress equals 58,000 pounds per square inch. The variable U is the reduction coefficient, which accounts for inefficiencies of transferring loads, and equals 0.85. The net area of the L-beam equals the gross area minus the area from the holes plus an area term accounting for diagonals in the failure path. From before, we already know the gross area equals 5.75 inches squared. The area of the bolt holes equals the number of bolt holes times the beam thickness, T, times the quantity, the diameter of a single bolt hole, plus 2 times the damaged thickness around the hole. Looking back at our L-beam, the problem stated that should a fracture failure occur, it would occur along path ABC, where path ABC includes 3 holes, A, B, and C. The thickness of a 6 by 6 by 1/2 L-beam equals 1/2 inch, and the hole diameter and damaged thickness are provided in the problem statement. The area from holes computes to 1.875 inches squared. The last term we need to solve for is the diagonal term S squared T over 4 times G. For the given failure path, there are 2 diagonal segments, AB and BC. Therefore, there will be 2 diagonal terms in the equation. After plugging in the stagger lengths and gauge lengths for the 2 paths, as well as the thickness of the beam, T, both diagonal terms equal 0.625 inches squared. And the net area for the beam equals 5.125 inches squared. Now we can solve for the nominal resistance of the beam resisting a fracture type failure, which equals 2.527 times 10 to the 5th pounds. And when multiplied by the resistance factor, also called the strength reduction factor, the design strength against fracture equals 1.895 times 10 to the 5 pounds. Since the failure mode with the smaller design strength governs the design strength of the beam, the design strength equals 1.863 times 10 to the 5 pounds. When reviewing the possible solutions, the answer is B.